Here's the second part of 9.3. Specifically, we're going to look at significance tests using a mean difference, which comes from pair data, which I will clarify. So comparative studies are more convincing than single sample investigations. And comparative studies include looking at two observations on the same individual or one observation of two very similar individuals, and that's called pair data. For example, we talked about a parking lot survey earlier in this unit. If a survey was randomly, 25 people or 100 people were randomly selected from the population and given the survey of how they felt about the parking lot situation, and then after the work had been done, those same 100 people were then surveyed again, that would be pair data, and you could look at the difference in their opinions, and that could also be looked at to see if it was statistically significant. You might look at comparing someone before they have done a specific exercise regime and after, keeping all sorts of things consistent, which is very difficult, but that would be paired. When paired data results from measuring the same quantitative variables twice, we can make comparisons with those differences. And of course, we have to meet our conditions, and if it has to do with means, then we'd use a one sample T procedure. If it had to do with proportions, we'd use a one sample Z procedure. But we can call them paired if it comes from paired data. So imagine you're researchers and you're interested in knowing whether caffeine affects depression. And so you're designing a study, and this is what the researchers decided to do. They recruited 11 volunteers who were diagnosed as being caffeine dependent. So they already had that in common. And then each subject, during the duration of the experiment, which is a 4-day experiment, they were barred from having any sort of substance that had caffeine in it. And during the 2-day period, the subjects took capsules containing their normal caffeine intake, and during the other 2-day period, they took placebo capsules. The order in which they took the caffeine or the placebo is randomized, and at the end of each 2-day period, there'd be a depression check. So let's say you were test subject A, and you were randomly chosen to get placebo on the first 2 days, then you would have your depression check. And then you didn't know it was placebos in the first 2 days. The second 2 days, someone knew because they gave you the caffeine. Then you'd have a depression check. So each person would have 2 pieces of data, how their depression checked out after their 2 placebo days and after their 2 caffeine days. So here are our 11 subjects. Here is their depression level on the 2 days that they had caffeine. And here's their depression level on the days they had placebos. And higher scores means higher depression symptoms. And so what they decided to do is they decided to find the difference, and they did placebo minus caffeine. So 16 minus 5 is 11, 23 minus 5 is 18, etc. So they found the difference there, and then we're going to use that information to go ahead and find, see if there's a significant, it's statistically significant, the difference on placebo versus caffeine. Little reminder, why did the researchers randomly assign the order in which the subjects received the placebo and caffeine? They wanted to be able to conclude that any statistically significant change in depression was due to the treatments themselves and not some other variable. So the obvious concern is the order of the treatment. Suppose the caffeine given to all the subjects during the first 2-day period. What if the weather was nicer on those 2 days than during the second 2 days? Or whether, there was other factors that could occur. The researchers wouldn't be able to tell if the depression was due to the weather or something else. And so by randomly deciding what days the different subjects had the placebo or the caffeine allows us to mitigate those other factors. Then they're going to go ahead and carry the test to investigate the question. So the data has been collected. The null hypothesis is that caffeine deprivation is going to have no effect on depression. And if that was so, then we would expect the difference between the depression scores to be 0. So our null in this case, notice there's a little d under our mu. The average depression score, the d does not stand for depression, but it stands for the difference in the placebo minus the caffeine. And then the researchers are expecting that caffeine depression is going to increase the depression scores. That's what they're expecting. And they've decided that they're going to go ahead and use an alpha of 0.05. So if the conditions are met, they can go ahead and do it. A paired t-test, because also it comes from paired data. So the researchers randomly assigned the treatments, and they randomly assigned the treatments. Okay. So the last check we have to do is our large sample check, and we don't know if the distribution of depression scores is normal. So we can't use that as our check. We don't have 30 or more in our sample, so we have to go ahead and look at the difference in depression scores. Now, in this particular case, we have 3 different ways of looking at the data. We have a histogram, a box plot, and a normal probability plot. This one, remember, if it's pretty close to a straight line, that shows us that the distribution is fairly normal. We want to check any of the 3 appropriate ones to find out if it's got a lot of skewness, or if it's got outliers, or if it's way off normal. We don't have to use all 3. So in this one, we don't see any specific normality, but we definitely don't see skewness or outliers. This one has a little bit of skewness, but it's not super strong, and this is pretty close to a line. So we can go ahead with our T procedures, but remember, you only need to choose one and show that there's not a lot of skewness or outliers. So we've run our one sample T test by finding the T value using our X bar minus the mu all over the standard error. And then we put that in our T table, and then we look in between the 2 and find the range. There's also ways of doing it on the calculator. This particular one we're going to talk about as well. You can take the list of the 11 differences, put them in, tell the computer to draw a t-test, and then it'll give you your test statistic, which we would have gotten from our calculation there as well. And then it'll give you your p-value. And it'll actually show you a picture of it. And in this case, the part that is under the curve is so small you can hardly even see it. And remember, this was a DF. You'll have to always tell that when you're talking about a T distribution, always have to tell the degrees of freedom, and -1. So in this case, because the p-value of 0.0027 is less than our alpha of 0.05, we reject the null. We have convincing evidence that the true mean difference, placebo minus caffeine, in depression scores is positive for subjects like these. Because we remember the null was the difference would be nothing. If the caffeine made no difference, if the placebo made no difference, there should be an average difference of 0. So carrying out significance test is pretty simple, but using test wisely is not so simple. And some points to keep in mind. Remember that a smaller alpha requires stronger evidence. So a smaller alpha of 0.01, it's going to talk about a tiny part of that tail could possibly happen by chance. And so if your values are over here, that's stronger evidence of a difference between the null and the alternative value. Higher power, which is your ability to accurately deem an alternative value true, you get a better chance of detecting that difference with a higher N and if that parameter of the null and the alternative value is farther apart. So if they're farther apart, it's easier to find. The significance level and desired power detecting a small difference is really quite challenging. And so if you're looking for, if you're looking at the depression of no difference in the depression scores with the caffeine and a difference of 1, and you want that to be your marker, it's going to be harder to find that, so you would probably need a larger sample than just the 11 that we had. Okay, I'm going to have us talk about multiple analysis in class, but statistical significance and practical importance. You can run a test, you can find statistical significance, but you might also find that the difference that is there, the tiny deviation, might not actually be practical to put into practice. And so, for example, they showed an example in the text about a cream that's supposed to help your wounds heal faster, and they went to the trouble to find 250 subjects, and they cut their arms, and they put cream on, and before the cream, it was expected that this kind of wound would on average take 7.6 days to heal, which meant the scab fell off. Get ready for that. They did find it was statistically significant to put on the cream every day that the people healed faster. But even though it was statistically significant at a 0.05 level, it really only healed faster by 0.1 day. So instead of 7.6 days, it was 7.5 days for the cut. Really not practically necessary to put on that cream then. So statistical significance doesn't necessarily mean it has a good practical application. And there we go.